All right, here I'm going to kind of jumble my notes a little bit because I think this goes better here. We're actually going to come back. I realize I just did section 18.5 and now I'm going to 18.7. We're going to come back to section 6. I'm not omitting it. It works better for me to do this first before I start talking about what's in section 6. So don't worry, I haven't forgotten it. We're coming back to it. Now, so let's talk about standard entropy changes for a reaction. We're going to call this delta S, 0 meaning standard state for the reaction. That means the change in entropy for a process in which all reactants and products are in their standard states. Remember what the standard states are. For a solid or liquid, that is 25 degrees Celsius, 298. So the temperature is always 25 degrees Celsius. Solid and liquid, pressure doesn't really matter. Gas and solution, pressure is always 1 atmosphere. And for a solution, 1 molar solutions. Those are the standard states. So that's it. That's going to be important later, but you do need to remember what the standard states are. We did go over these in chapter 6, so you can review back there. Turn the page. Standard molar entropies. This is where we're talking about delta S, 0. Standard molar entropies. So we've done this before with delta H's. Remember when we did delta H0? So it's similar but different. Unlike when we had standard enthalpy, that was delta H0, where we just assigned a value of 0 to elements in their standard state because it was kind of relative. We didn't really have an absolute. We just needed somewhere to go. However, there is an absolute 0 entropy. That's a difference here. Which brings us to the third law of thermodynamics, which says the entropy of a perfect crystal at absolute 0, which is 0 Kelvin, is 0. There is absolute 0 entropy. So entropy is also, so we said it's a state function. How you get there doesn't matter, but it is what is considered an extensive property, which means it depends on the amount of substance there is. So standard entropies are found in the reference tables. There's some in the back of the book. And the units for entropy are always in joules per mole Kelvin. So what you're going to need is you're going to make sure you bring or reference your tables when you're working on these problems. Here's my book. And it's going to be in one of these appendices. Back here, I believe it's Appendix 2. Yeah, here's Appendix 2, useful data. All right, remember I showed you these before? We had the substance and we looked at heat of formations when we were doing that. Here, over here in the third, S0 entropy, joules per mole Kelvin. And notice all of these are positive. All right, so just make sure that you look at the correct units in the correct column when you do that. You will need these reference tables. They're available in the online text as well. And they're arranged in alphabetical order by the first element. So you will need those. When I'm working these problems, I may or may not show you exactly where those are. But just know you need to have those. On a test, of course, I'm going to give them to you. You know, that's not something you'll never be required to memorize entropies of standard entropies or anything. Okay, so relatively compared to each other, entropies are going to be highest for gases. Gases are going to be higher than liquids, and liquids are going to be higher than solids. Think about particle arrangement. This is pretty intuitive. Now, entropy also increases with increasing molar mass of an elephant. You don't need to worry about why. There's a detailed explanation in the book if you care about it, but this is a take-home point. Higher molar mass, greater entropy. Molecules generally have more entropy than free atoms. And more complex molecules have more entropy than simpler molecules. And then an aqueous solution of a substance has more entropy than its crystalline solid. Because remember, the particles are going to decrease, so related to moles, number of moles in solution more than number of moles in the solid. If you care about why, read about it in the book. That's the take-home point. All right, so let's talk about how to calculate the standard entropy change of a reaction the same way as we do Hess's law. So, change in the reaction is going to be change in standard entropy of the products minus change in standard entropy of the reactants. Y'all usually did very well with Hess's law, so I think you'll do fine here. All right, so let's use some words. That means we're going to subtract the standard entropies of the reactants that are multiplied by their, everybody's favorite word, stoichiometric coefficients from the standard entropies of the products, lost where it was, multiplied by their stoichiometric coefficients. All right, so this is going to look similar. So delta S0 reaction, summation, moles products times delta S0 of the products minus summation moles reactants times delta S0 reactants. And how did I tell you we remember the order? Because P comes before R. Oh, I got reactants way excited up there. So products minus reactants, P before R. All right, so the reverse of an equation. Make sure you can identify what are the products and what are the reactants. It's an important skill. And N always equals the coefficients in a balanced equation. Now, unlike our enthalpy calculation, standard entropies are always positive at 25 degrees Celsius. That tends to make the math a little bit easier. We don't have to carry out some negatives, because the only time can we ever have a negative entropy? No, we cannot have negative entropy. There is an absolute zero entropy, and that is a perfect crystal at absolute zero is zero. So entropies should always be positive. Now, be careful about that. If you find yourself writing down a negative entropy, you're probably looking at the wrong column. Double check yourself. All right, so let's do an example. Here's our chemical equation. 4 moles of ammonia, 5 oxygens, 4 mononitrogen or nitrogen monoxide, and 6 water vapors. All right, look, all of these are positive. All right, so let's do this. Summation. Whoa, that's a bad looking summation. All right, so we're gonna say delta S0 reaction, and here we're gonna have N delta S products, or it doesn't have to be delta S, but minus summation of N S0 reactants, the one in the table. All right, so products. Again, start your brackets, open the bracket. Our first product, nitrogen monoxide, 4 moles. And I like to go ahead and write the units here. And here, nitrogen monoxide, so 210.8 joules per mole Kelvin. Plus, we have another product, 6 moles. Look on the chart, 188.8 joules per mole Kelvin. That's all the products. Close the bracket. Minus. Open the bracket. Reactants. First one, 4 moles. Ammonia up here, 192.8 joules per mole Kelvin. Plus oxygen. So 5 moles. Whew, almost out of room. Times 205.2 joules per mole Kelvin. All right, close the bracket. All right, let's cross out all our moles. Do that first. Okay, because remember, we should always be in joules per Kelvin. All right, so I'm just going to work on these brackets one by one. Again, you can probably do this in the calculator in one step because you're better at parentheses than I am, but that's okay. I recognize my limits. Plus 6 times, actually here, let me do it this way, 4 times 210.8. So 843.2 joules per Kelvin plus 6 times 188.8. Again, you can do this in one step if you want to. But since I'm doing this as an example, I figure you can follow me for the entire process. 192.8, 771.2 joules per Kelvin plus 5 times 205.2, so 1026 joules per Kelvin. All right, so now 843.2 plus 1132.8, 1976 joules per Kelvin minus 771.2 plus 1026. 1797.2 joules per Kelvin. And I'm going to go ahead and 1976 minus that answer. I got 178.8. 178.8 joules per Kelvin. Is this a spontaneous process? Yes, it is, because this is positive. Entropy is positive. So its question didn't ask this, but you can practice. Yes, this would be spontaneous. All right. Again, remember Hess's law. You can do this. It's not that hard.